After you got this heavy dose of mathematics and equation that we started very simply with the harmonic oscillator, I wanted to take you through a VMDL, which is rather simplistic VMDL, but it's about temperature. The reason I'm showing you that because it connects directly with the kinetic energy part, which is half mv square, and how does that connect with the temperature variations. So this is a movie which is a pre-recorded VMDL simulation, and I would encourage you to go there and sort of answer some of the questions that are embedded. So this is a system of 25 particles, and we are using them as a simple particle with certain velocity and certain potential energy function, which gives them certain spring constant. And then we start with playing with the temperature by kinetic energy. So you see 25 particles, low temperature. Pay attention to the velocities. So you are looking at the velocities. Let's look at kinetic energy, and let's see temperature. So we will, let's put some temperature first. Let's see. So we are going to start with certain temperature, which is a low temperature. Now we are going to increase temperature by 10 times. So as you increase the temperature, now you see that the kinetic energy has gone up. Now let me show the averages and show real units, and let's start again. So now in this case the particles by absolute kinetic energy. So if you look at the absolute kinetic energy of the particle, spectrum, now you can see the spectrum in terms of what are the different colors here. So the red color shows you the very low kinetic energy. As you go, violet is the highest kinetic energy. So you can see some particles here which are violet, some of them are yellow, some of them are green, the middle part of the kinetic energy spectrum, and some of them are really slow, which is the red part of the kinetic energy spectrum. So now you are looking at the display of how these kinetic energies are distributed. So half mv square is now distributed among 25 particles. So you move again, which molecule move faster, the red, green or violet. So now if you look at the red particles have smaller kinetic energy, violets have very high energy. So obviously they will move much faster velocities. Now you move forward again. Now we decrease the temperature by a factor of 10. So now if you see here, we are decreasing the temperature factor of 10, and see the change in the colors. So the colors have changed to red side, which is the lower kinetic energy, as you change the temperature by rescaling the velocity in molecular dynamics. So as you know, the rescaling velocity in our MD code we had looked at, and that connects with the kinetic energy part, only kinetic energy part we are looking at. And then you look at here that now you can count how many particles are different colors do we have now. If you look at here, not too many of them are different color, because they are all gone to the lower velocities as you go forward. So let's rewind this again. So now we looked at, there are two parts here. One is we go to very high temperature 10 times, and then we also drop it down to 10 times. So now let's look at kinetic energy function here and see how it moves as we move to this. So now you can see the change in the kinetic energies. So initially, as you can see, they are at 0 velocity, all of them are red. We let them go. So now you can see that there is some change. Now we increase the temperature, rescaled it. So now you can see there is all kinds of velocity distribution based on the Boltzmann distribution, and what we looked at, the simple harmonic motion here for the particles where they are getting more and more energy. Now go further down. So we are moving ahead with the absolute kinetic energy spectra, and then at certain point we drop down the temperature and the color goes down, and you can also see the kinetic energy following the same model. Now if you look at, so we have energy, where now we are looking at kinetic and potential energy. So let's rewind it and see what happened in the same concept, where we have the two terms which we looked at for the spring dashpot model, kinetic energy term, and we looked at the potential energy curve. So at the 0 temperature, we are starting with very low kinetic and potential energy. Kinetic is red and potential is blue. Start. So, now you can see that the kinetic energy and potential energy variations. As we increased it, you can see the kinetic energy went way far, but because there is no, these are all unbonded materials, you are looking at that the potential energy is remaining low, and configuration has no effect here primarily because they are all randomly placed. So, summation of all potential energy is same, but kinetic energy velocity is increasing quite a bit. So, now when we drop it, so now we drop the kinetic energy, it goes back to the drop level, and if you look at here, you can see that the relation between the two plots, which is very clear. We saw also in two particle system that you have this kinetic energy goes up, potential energy goes down, which is the equation that we derived. And so, they have almost mirror replica in terms of as the amplitude goes up for the kinetic, the amplitude for potential energy goes down, and vice versa. And that is what we had developed in our simplistic model for the particles. So, let me stop here, and now we are going to jump into vibrational modes and how they connect with the velocity autocorrelation function. Thank you.